On a clear, moonless night, the sky reveals itself as a grand tapestry, sprinkled with countless points of light. Our intuition tells us a simple story, that the brightest of these celestial diamonds must surely be our closest companions in the cosmic dark. We gaze up at brilliant beacons like Sirius, the dog star, which dominates the winter sky, and we feel a sense of proximity. Yet, in the vastness of space, our senses are easily deceived. The universe does not place its brightest lamps in the front window. Our true, stellar neighbor, the star that lies closer to our own sun than any other, is a celestial ghost, so faint and unassuming that it remained completely invisible to every human who lived and died before the dawn of the 20th century. This shared spectacle of the night sky connects us all, across every continent and every time zone. It's a humbling and inspiring sight, and we would love to know where you're listening from and what time it is for you. So please do leave a comment for us. And if you enjoy pondering these grand cosmic mysteries, be sure to subscribe so we can notify you when our future stories are released. The story of our nearest neighbor begins not with a brilliant flare, but with a quiet revelation. This star is named Proxima Centauri, a faint red dwarf nestled within the southern constellation of Centaurus. It is a member of a trio of stars, yet it is utterly unseen by the naked eye, a cosmic whisper next to the stellar shouts of its two far brighter companions, Alpha Centauri A and B. To speak of it as a neighbor is to embrace a scale that defies human comprehension. It lies just over 4 light years away, a journey that for light itself takes more than 4 years to complete. This distance translates to a staggering 40 trillion kilometers, or about 25 trillion miles. It is a void so immense that if our own sun were the size of a front door in London, Proxima Centauri would be another, slightly smaller door, all the way in Cairo. This is the true nature of interstellar space, not a short walk across the street, but a chasm of cold, empty darkness separating us from even our very closest stellar family. The light that leaves its surface today will not arrive at Earth until many years have passed. This, then, is the story of that faint, red star. It is a narrative that begins with a determined astronomer in South Africa, peering at photographic plates and noticing a tiny anomaly. It is the story of a star that is both ancient and violent. A star that could live for trillions of years, yet frequently lashes its surroundings with furious radiation. And most compellingly, it is the story of the worlds we have recently discovered in orbit around it, planets that exist on the very edge of possibility, sparking one of science's most profound questions. Could life exist on a world so different from our own, yet so tantalizingly close? This is the story of our silent neighbor, a neighbor that has been waiting patiently for us to look past the glare and notice the quiet invitation it offers into the great, dark expanse beyond our home. That quiet invitation, hanging in the deep southern sky, would not be answered by a grand expedition or a sudden flash of insight, but by the patient, methodical work of one man who had dedicated his life to the subtle movements of the stars. Our story moves now from the abstract realm of cosmic distance to the crisp, thin air of the South African Highveld, just over a century ago. The man who would redraw the map of our stellar neighborhood was Robert Thorburn Ayton Innes, a figure whose path to astronomical greatness was as unconventional as the star he would discover. Born in Edinburgh, Scotland, Innes was not a product of formal university training. He was a self-taught enthusiast, a wine merchant by trade, who spent his nights in Australia gazing at the southern skies. His passion for the intricate dance of double stars burning far brighter than his career in commerce. His meticulous observations and catalogs of binary star systems earned him such a reputation that, despite his lack of academic credentials, he was invited to South Africa and eventually became the first director of the newly established Transvaal Observatory, later renamed the Union Observatory, perched on a hill overlooking the burgeoning city of Johannesburg. This location, at an altitude of over 1,800 meters, or nearly 6,000 feet, offered astronomers exceptionally clear and stable atmospheric conditions, a perfect window through which to conduct the painstaking work of charting the heavens. It was here, amidst the political tumult of the early 20th century, that Innes would turn his attention to the Alpha Centauri system, a celestial jewel he knew intimately, suspecting that its secrets were not yet fully revealed. Innes was a master of a technique that had revolutionized the search for celestial objects that move. He possessed an instrument known as a blink comparator, a marvelous optical device that allowed for the rapid viewing of two different photographic plates of the same region of sky, taken at different times. These were not digital files, but large, delicate plates of glass coated in a light-sensitive emulsion, each one a frozen moment of celestial history. The principle behind the blink comparator was elegantly simple, yet powerfully effective. When the observer looked through the eyepiece, the machine would present first one plate, then the other, in quick succession. For the tens of thousands of stars in the field of view that were immensely distant, their positions would be identical on both plates, and they would appear perfectly static. But if any object was significantly closer to Earth or moving at a high velocity, its position against the backdrop of more distant stars would have shifted in the intervening years between the two exposures. This object would appear to jump or blink with each flick of the machine, instantly betraying its unique status. This was the work of an astronomical detective, hunting for a single moving suspect in a crowd of millions. In 1915, Innes began a systematic search using this very method on a series of plates centered on Alpha Centauri. One set of images had been captured in 1910, providing a 5-year interval for any nearby star to reveal its motion. The process was grueling. It required hours of intense concentration, sitting in the dark, peering into an eyepiece, his mind trained to catch the slightest flicker of movement in a sea of overwhelming stillness. He was comparing a new plate he had just taken with one captured years earlier by the astronomer John Franklin Adams. When he saw it, in a region of the sky crowded with faint stellar points, one insignificant speck of light, too dim to warrant any special attention on its own, did not hold its position. With every flick of the comparator, as the view switched from the 1910 plate to the 1915 plate, this single, unremarkable starlet leaped back and forth. It was the telltale sign of high, proper motion, the apparent drift of a star across the celestial sphere. But what made Innes's heart race was not just that it was moving, but the direction and speed of its movement. He quickly performed the calculations, and his suspicion was confirmed. This faint star was moving across the sky at almost precisely the same rate and in the same direction as the famous Alpha Centauri A and B. It was like finding a tiny, unnoticed boat drifting with the same current and speed as two massive, well-known battleships. The implication was profound and immediate. This was no coincidence. This dim star was not a random wanderer, but a physical companion to the Alpha Centauri system, a third member of the family, bound by gravity and traveling with them on their immense journey through the Milky Way galaxy. In a quiet, darkened room, as the First World War raged thousands of kilometers away, Robert Innes had discovered that our closest stellar neighbor was not a bright binary, but a trio. The discovery was a triumph of patience and precision. Innes continued to observe the faint star and his subsequent measurements of its parallax. The tiny shift in its apparent position caused by the Earth's own orbit around the Sun delivered a second, even more startling revelation. Not only was this star a companion to Alpha Centauri, but it was slightly closer to us. The parallax angle was just fractionally larger, indicating a distance of roughly 4.22 light years, about 1/10 of a light year, or nearly 1 trillion kilometers, closer than its brilliant siblings. 2 years after his initial observation, in a 1917 paper, Innes suggested a name for this newly found star, a name that perfectly captured its significance: Proxima Centauri. The name is derived from Latin, with proxima meaning the nearest to, or closest. With that simple, elegant name, the celestial order was reshuffled. The title of the Sun's nearest stellar neighbor was transferred from one of the brightest and most celebrated stars in the night sky to a feeble, reddish ember with less than 1/10,000th of the Sun's luminosity. The discovery was a humbling lesson in cosmic perspective. It demonstrated that the universe does not always advertise its most proximal wonders with brilliant displays. Sometimes, the most profound secrets lie hidden in the faint whispers of light, waiting for a persistent observer to finally notice. Innes had not just found a star. He had given humanity a new next-door neighbor. And in doing so, he opened the door to a new set of questions about the nature of this dim, mysterious world that was now officially the closest star to our own. Those questions about the nature of our new neighbor would lead astronomers down a path that revealed an entirely new class of celestial object. A type of star so fundamentally different from our own that it forces us to reconsider the very definition of a sun. Proxima Centauri is a red dwarf, the most common type of star in the Milky Way, yet one that operates on principles and timescales that are almost alien to our experience. To understand this faint star is to understand the quiet, slow-burning majority of the galaxy's stellar population. If our sun is a roaring bonfire, a brilliant and hot blaze that consumes its fuel with ferocious intensity, then Proxima Centauri is a smoldering ember. It is a star in miniature, possessing only about 1/8 of the sun's mass. This might not sound dramatically small, but in the world of stellar physics, mass is destiny. This lack of heft means it is also physically tiny, with a diameter of about 200,000 kilometers, or roughly 124,000 miles. This makes it only about 1.5 times the size of the planet Jupiter, a gas giant in our own solar system. Imagine that, a fully functioning, hydrogen-fusing star, a celestial engine of immense power that is barely larger than a planet. This diminutive size is the primary reason for its ghostly faintness. Its surface temperature is a mere echo of our sun's. While the surface of our star burns at a blistering 5,500 degrees Celsius, which is nearly 10,000 degrees Fahrenheit, Proxima Centauri's surface is a comparatively placid 2,770 degrees Celsius, or just under 5,000 degrees Fahrenheit. This lower temperature dictates the color and nature of the light it emits. It shines with a dull, ruddy glow, and the vast majority of its energy is radiated not as visible light, but as invisible infrared heat. To human eyes, it is almost a phantom, but in the infrared spectrum, it shines with a more determined, if still modest, light. This inherent dimness means that even though it is our closest neighbor, it is 100 times too faint to be seen with the naked eye. If Proxima Centauri were to replace our sun at the center of our solar system, our daylight would be as dim as a softly lit room, and its reddish disk would appear huge in our sky, a smoldering crimson eye in a perpetual twilight. The Earth would be a frozen ball of ice, its oceans locked in a permanent, silent winter. The difference in energy output is staggering. While it is our closest neighbor, it delivers to us across the 4.2 light-years of space less light than a single candle would from a distance of 20 kilometers, or about 12 miles. The true secret to Proxima Centauri's nature, however, lies deep within its core. A star like our Sun is structured in layers, like a celestial onion. At its center is a radiative zone, where energy from nuclear fusion slowly pushes its way outwards over hundreds of thousands of years in the form of photons. Only in its outer layers does the energy begin to churn in vast, boiling cells of plasma, a process called convection. Proxima Centauri is different. Its low mass means it is not layered in this way. Instead, it is fully convective. From its very core to its surface, the entire star is in a constant, slow, roiling motion, like a pot of thick soup simmering on a cosmic stove. This perpetual churning has a profound consequence. In the Sun, the helium ash produced by hydrogen fusion is steadily accumulating in the core, and in another 5 billion years, this buildup will cause the Sun to swell into a red giant, eventually destroying it. Proxima Centauri, however, is constantly stirring its fuel. The helium ash is mixed throughout the star, and fresh hydrogen from the outer layers is continuously cycled down into the core. This makes it incredibly efficient. It doesn't just burn the fuel in its core, it is able to use almost its entire supply of hydrogen over its lifetime. This efficiency gives red dwarfs a lifespan that is difficult to truly comprehend. Our Sun is expected to live for a total of about 10 billion years. Proxima Centauri, burning its fuel with such miserly slowness, is predicted to remain a stable, hydrogen-fusing star for an astonishing 4 trillion years. That is nearly 300 times the current age of the entire universe. When our Sun dies, when the Andromeda Galaxy has long since collided with our own, when countless generations of larger, brighter stars have been born and have perished in spectacular supernovae, Proxima Centauri will still be shining with its gentle crimson light, still in its stellar infancy. It is a living fossil from the universe's youth that will far outlive almost everything we see in the sky tonight. It represents a form of near immortality on a cosmic scale. Yet this image of a placid, eternal ember is a dangerously incomplete one. The slow, stable interior of Proxima Centauri belies a chaotic and violent surface. Because of its deep convection and rapid rotation, the star generates an incredibly powerful and tangled magnetic field. This field frequently breaks through the surface, snapping and reconnecting in events that unleash colossal bursts of energy. Proxima Centauri is what is known as a flare star. Without warning, its brightness can surge dramatically. In a matter of minutes, it can become hundreds or even thousands of times brighter than its normal state. These are not gentle flickers. They are cataclysmic explosions. One major flare observed in 2019 caused the star to become 100 times brighter in ultraviolet wavelengths over just a few seconds. These flares are accompanied by massive releases of high-energy X-rays and streams of charged particles, washing the surrounding space in a torrent of lethal radiation. In fact, Proxima Centauri's average X-ray output is roughly the same as our much larger sun's. And during a flare, its X-ray luminosity can increase 1,000-fold. This reveals a chilling paradox. While the star's interior promises stability on a trillion-year timescale, its surface is one of the most hostile and unpredictable environments imaginable. It is a tiny dragon, mostly slumbering, but occasionally breathing bursts of ferocious fire. This violent nature profoundly changes the conversation about its potential to host life, transforming what might seem a cozy campfire into a dangerously unpredictable inferno. This dual identity, the ancient, steady furnace on the one hand, and the raging, unpredictable magnetic engine on the other, is the central mystery that defines our nearest stellar neighbor, and it sets a dramatic stage for the next phase of our story: the search for planets caught in the dance of this crimson sun. But before we can seek out the planets caught in that dance, we must first understand the dance itself. For Proxima Centauri does not move through the void alone. It is a minor player in a much grander and more ancient ballet, a performance on a stage so vast that a single step takes 500,000 years to complete. To appreciate the story of Proxima is to lift our gaze from that single, faint star and behold the magnificent celestial partnership it keeps. Its companions are Alpha Centauri A and Alpha Centauri B, and together these three stars form the Alpha Centauri system, a complex and gravitationally bound family. It is a system that has captivated stargazers for centuries, long before anyone knew of its tiny, invisible third member. Seen from the southern hemisphere, Alpha Centauri is not a single point of light, but the third brightest star in the entire night sky, a brilliant, golden-hued jewel that outshines all but Sirius and Canopus. For most of human history, this was the entire story: a beacon in the constellation Centaurus that guided navigators and inspired myths. It was only with the invention of the telescope that we discovered this single beacon was, in fact, two stars, locked in an intimate embrace. Alpha Centauri. A is a star remarkably like our own sun. It is a G-type main sequence star, just a little larger and about 1.5 times more luminous than the star that warms our own world. If it were at the center of our solar system, we would scarcely notice the difference, perhaps a slightly brighter, yellower daylight. Its companion, Alpha Centauri B, is a K-type main sequence star, a little smaller and cooler than the sun, shining with a distinct orange tint. It emits only about half the sun's light. These two sun-like stars perform their own, much tighter dance, a celestial waltz at the heart of the system. They are bound in an orbit that takes them just under 80 Earth years to complete, a single human lifetime. Their orbit is not a perfect circle, but a pronounced ellipse, which means the distance between them changes dramatically. At their closest approach, they are separated by about 11 astronomical units, a distance that would place them roughly as far apart as the Sun and Saturn in our own solar system. At their most distant, they swing out to over 35 astronomical units, a gap similar to the distance between our Sun and Pluto. From a hypothetical planet orbiting either star, the other would not be a mere point of light, but a dazzlingly brilliant disk in the sky. A second, distinctly colored sun, capable of casting its own shadows and painting the landscape in alien hues of orange and gold. This dynamic, sun-like pair is the system's radiant and powerful core. It is against this backdrop of two dancing, sun-like stars that we must place Proxima Centauri. Our faint red dwarf is the distant, solitary outlier of this family. The distance that separates Proxima from the central binary pair of A and B is almost impossible to visualize. It is not a short stroll across a celestial field. It is a journey across an immense, dark ocean. Proxima lies at a staggering distance of about 13,000 astronomical units from its parent stars. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers, or 93 million miles. Multiplying that by 13,000 gives a separation of nearly 2 trillion kilometers, or well over 1 trillion miles. This chasm is so vast that it takes light over 7 weeks to travel from the central pair out to Proxima. For a long time, this enormous separation caused a deep debate among astronomers. Was Proxima Centauri truly a part of the Alpha Centauri family, bound by their gravity? Or was it merely an unrelated star that happened to be passing by at this particular moment in cosmic history? A temporary neighbor on an independent journey through the galaxy? The initial clue, the one that Robert Innes had seized upon, was that they shared the same proper motion. They were all sailing in the same direction across the sky. But this was not definitive proof. It could still have been a remarkable coincidence. The final, conclusive evidence came in the late 20th and early 21st centuries, with the advent of incredibly precise instruments like the Hipparcos satellite and the Hubble Space Telescope. These instruments could measure not just the sideways motion of the stars across the sky, but also their radial velocity, their speed directly towards or away from us, with unprecedented accuracy. The data confirmed it beyond any doubt. All 3 stars are moving through the Milky Way together as a single, gravitationally coherent unit. Proxima Centauri is not a passerby. It is a true, albeit incredibly distant, member of the family. Its orbit around the central A and B pair is a slow, majestic procession that takes roughly 500 147,000 years to complete just once. Dinosaurs walked the Earth during Proxima's previous circuit, and modern humanity may no longer exist when it completes its next. During this immense orbit, its distance from the central pair varies, from a close point of about 4,300 astronomical units to a distant swing of over 13,000. We happen to be living in an era when Proxima is near its farthest point in this epic journey, and also at a point in its orbit that coincidentally places it slightly closer to our own solar system than its two brilliant companions. For the next 30,000 years, Proxima will retain the title of our nearest stellar neighbor, a temporary crown it wears on its half-million-year pilgrimage around the heart of its own solar system, a heart that lies a quarter of a light year away. This grand, slow dance defines the environment of our closest star. It is a star that lives a life of profound isolation, yet is forever tethered to its brighter siblings. This cosmic arrangement, a tiny, volatile red dwarf orbiting a brilliant binary pair from an immense distance, creates a unique celestial laboratory. And it was only a matter of time before astronomers turned their most powerful tools upon that faint red dot, asking the ultimate question: in this complex and ancient system, did Proxima Centauri manage to hold on to any worlds of its own? That question of whether Proxima Centauri held worlds of its own lingered in the astronomical community for a century after its discovery, a tantalizing but seemingly unanswerable puzzle. For decades, the answer was silence. The faintness of the star and the immense distances involved meant that our methods for finding planets, or exoplanets as they are known, were simply not up to the task. The most common techniques were ill-suited for this specific challenge. Directly imaging a planet around Proxima would be like trying to spot a firefly hovering next to a distant searchlight. The feeble, reflected light of any world would be utterly lost in the glare of its parent star, faint as that star might be to us. Another powerful method, the transit technique, which watches for the tiny dip in a star's light as a planet passes in front of it, also faced long odds. It requires a precise edge-on alignment of the planetary system relative to our line of sight, a specific cosmic geometry that is statistically rare. Furthermore, Proxima's own violent nature, its tendency to flare and change in brightness, would create a storm of false signals, making the subtle shadow of a transiting planet nearly impossible to distinguish from the star's own intrinsic flickering. To find a world around our nearest neighbor, astronomers needed a different tool, one that listened not for a shadow, but for a whisper of motion, a tool of almost unbelievable sensitivity. The key lay in a method known as the radial velocity technique, a beautifully indirect way of sensing a planet's presence. This technique does not look for the planet itself, but for the subtle effect the planet's gravity has on its star. A planet does not simply orbit a star. Rather, the planet and the star both orbit their common center of mass, a point known as the barycenter. Because the star is so much more massive, this point lies deep inside the star itself, but it is not at its exact center. This means that as the planet makes its journey, the star is also performing its own tiny, corresponding orbit. It is not stationary. It wobbles. From our vantage point, 4.2 light-years away, we could never hope to see this minuscule wobble directly, but we can detect its effect on the starlight we receive. This is where the Doppler effect comes into play, the same principle that causes the pitch of an ambulance siren to rise as it speeds towards you and fall as it speeds away. As Proxima Centauri wobbles, it moves slightly towards us in its tiny orbit, and the waves of its light get compressed, shifting ever so slightly towards the blue end of the spectrum. Then, as it swings around and moves slightly away from us, the light waves are stretched, shifting towards the red. This rhythmic back and forth, this cosmic pulse, is the fingerprint of an unseen planet. The challenge, however, was one of scale. The wobble induced by a small, Earth-sized planet would be incredibly gentle, causing the star's velocity to change by only a few meters per second, the speed of a brisk walk. Detecting such a subtle shift in the light from a distant star required an instrument of staggering precision. That instrument was the high-accuracy radial velocity planet searcher, or HARPS, a spectrograph attached to the European Southern Observatory's 3.6-meter telescope at the La Silla Observatory. Perched high in Chile's bone-dry Atacama Desert, at an altitude of 2,400 meters, or nearly 8,000 feet, this observatory sits under some of the clearest, most stable skies on Earth. The HARPS instrument is a masterpiece of engineering, a machine designed to do one thing with more precision than any other device on the planet: to split starlight into its constituent colors, its spectrum, and measure the Doppler shift with an accuracy that can detect a motion of just 1 meter per second. In 2016, a team of astronomers led by Guillem Anglada Escudé of Queen Mary University of London launched a dedicated campaign called the Pale Red Dot. The name was a deliberate, poetic echo of Carl Sagan's famous pale blue dot description of Earth. The goal is to stare at Proxima Centauri night after night for nearly 3 months, accumulating enough data to either find the signal of a planet or rule out its existence once and for all. It was a high-stakes effort. They were fighting against the star's own natural volatility, carefully filtering out the noise from its flares and star spots to listen for the faint, regular heartbeat of a planetary companion. Night after night, the data streamed in, and slowly, painstakingly, a pattern began to emerge from the static. It was a clear, persistent, and gentle sine wave in the data, the unmistakable signature of a star being tugged back and forth. The signal repeated with a period of just 11.2 Earth days. This was it. After a century of speculation, the evidence was undeniable. Proxima Centauri was not alone. The team's calculations, based on the amplitude of the wobble, revealed that the unseen world had a minimum mass of just 1.3 times that of Earth, suggesting it was very likely a rocky, terrestrial planet. And its swift 11.2-day orbit meant it was incredibly close to its star, orbiting at a distance of only 7.5 million kilometers, or about 4.7 million miles. This is just 5% of the distance between the Earth and our Sun. In our solar system, a planet this close would be a scorched, lifeless cinder, its surface hot enough to melt lead. But Proxima Centauri is a cool red dwarf. At this close proximity, the planet was receiving just enough warmth to place it squarely within the star's habitable zone, the tantalizing orbital region where temperatures might be just right for liquid water to exist on its surface. On August 24th, 2016, the discovery was announced to the world, and the news became an instant global phenomenon. Humankind had discovered its closest exoplanet. It was not a distant gas giant or a fiery inferno, but a small, potentially rocky world in the habitable zone of the very next star. The planet was officially named Proxima Centauri b, and its discovery transformed our silent neighbor into the host of the most compelling and accessible alien world in the known universe, opening a thrilling new chapter of inquiry and imagination. This new chapter of inquiry and imagination, however, began not with triumph, but with caution. The discovery of Proxima Centauri b was a watershed moment, but the label habitable zone is a dangerously seductive one, a simple line drawn in the sand of a cosmic desert that promises an oasis. The reality is far more complex. The zone merely defines a region where the energy received from a star is moderate enough for the surface temperature of a planet with an Earth-like atmosphere to allow for the existence of liquid water. It is a first, crude filter in the search for life, but it says nothing of the true conditions on the ground. As scientists began to model the environment of this newfound world, the initial, heady optimism was quickly tempered by the harsh and alien physics of a planet orbiting a red dwarf star. The first and most profound challenge arises from the planet's sheer proximity to its sun. An orbit of just 11.2 days places it deep within the star's gravitational well, and this intimacy has an inescapable consequence: tidal locking. Over billions of years, the relentless gravitational pull of Proxima Centauri would have tugged on its nearby planet, slowing its rotation until it became synchronized with its orbit. This is the same phenomenon that has caused our own moon to always show the same face to the Earth. For Proxima b, this means one hemisphere is trapped in perpetual daylight, forever scorched by the crimson sun, while the opposite hemisphere is locked in an endless, frozen night. This creates a world of two extremes: a planet with a permanent day side and a permanent night side. The substellar point on the day side, the spot directly beneath the star, would be a landscape of unrelenting heat, where any water would have long since boiled away into the atmosphere. The night side, conversely, would be a realm of unimaginable cold, a landscape so frigid that the very air itself could freeze, snowing out onto the surface as nitrogen and carbon dioxide ice, potentially stripping the planet of its atmosphere altogether. The hope for life, then, lies not in these two inhospitable zones, but in the narrow ring of perpetual twilight that separates them. This is the Terminator Zone, a world-circling ribbon of land and perhaps ocean where the red sun would hang forever on the horizon, bathing the landscape in a permanent, dusky red dawn. Here, temperatures could be moderate, potentially allowing liquid water to pool and flow. Yet even this sliver of temperate real estate would be a land of extremes. The immense temperature difference between the hot day side and the cold night side would likely drive ferocious planet-girdling winds as the atmosphere desperately tried to equalize the temperature. The sky above the Terminator Zone might be a place of perpetual, raging storms, a place far more violent than any hurricane on Earth. Life in such a place would have to be incredibly resilient, adapted to constant gales and a sky that never changes. But even if life could find a foothold in this twilight zone, it would face a far greater, more existential threat, one that comes not from the planet, but from the star itself. As we have seen, Proxima Centauri is a flare star, a magnetically volatile beast that unleashes furious tantrums of radiation. For a planet orbiting at a distance of only 7.5 million kilometers, or just over 4.5 million miles, there is nowhere to hide. When the star erupts, Proxima b is engulfed in a cataclysmic flood of high-energy X-rays and ultraviolet radiation. The levels of X-ray radiation during a superflare could be hundreds of times greater than what the Earth receives from our much quieter sun. Any life on the surface would be sterilized, its complex organic molecules shredded by the onslaught of energetic photons. Furthermore, these flares are accompanied by coronal mass ejections, which hurl vast clouds of charged particles into space. This stellar wind, supercharged during a flare, would slam into the planet's atmosphere. Over millions and billions of years, this process, known as atmospheric stripping, could have eroded away the planet's protective gaseous envelope entirely, leaving behind a barren, airless rock, much like Mars in our own solar system. The only plausible defense against such an assault would be a powerful, global magnetic field. A magnetosphere, like the one that protects Earth, could deflect the majority of the incoming charged particles, shielding the atmosphere and the surface from the star's most violent outbursts. But we have no way of knowing if Proxima b possesses such a shield. And even if it does, the sheer intensity and frequency of Proxima Centauri's flares might be enough to overwhelm it. The planet is caught in a terrible catch-22. It must be close to its cool star to be warm enough for liquid water, but that same proximity exposes it to a level of stellar violence that could render it completely uninhabitable. And finally, even the light itself presents a challenge. Photosynthesis on Earth has evolved over billions of years to be perfectly tuned to the spectrum of our sun's light, which is rich in yellow and green wavelengths. Proxima Centauri, a red dwarf, emits most of its energy in the red and infrared parts of the spectrum. Life on Proxima b would require a completely different kind of biochemistry to harness this low-energy light. Perhaps plants there would be a deep, dark, black, evolving pigments that could absorb energy across the entire available spectrum just to survive. The thrilling discovery of Proxima b did not, in the end, give us a picture of a second Earth. Instead, it painted a portrait of a world on a knife's edge, a planet of stark contrasts and profound dangers. It forced us to confront the reality that the galaxy's most common stars may host the galaxy's most challenging environments for life. The question was no longer simply whether a planet existed in the right place, but whether that planet had won a series of cosmic lotteries against almost insurmountable odds. The initial, simple hope had given way to a more complex and fascinating puzzle, one that pushed astronomers to keep looking, to see if Proxima b was the only world in this system, or if it had siblings that might tell a different story. That different story began to unfold not with a new, frantic search, but through the patient re-examination of old clues, a deep dive back into the very same data that had revealed Proxima b. The discovery of the first planet was a triumph, but its powerful signal, that clear 11.2-day pulse, had acted like a loud drumbeat in a quiet room, making it difficult to hear any subtler, fainter melodies that might also be present in the data. Astronomers knew that the star's own violent flaring and boiling surface created a significant amount of statistical noise. Hidden within this stellar static, and masked by the strong signal of Proxima b, could be the whispers of other worlds, the gravitational nudges of siblings that were either much smaller or much, much farther away. For years, teams of scientists meticulously sifted through the accumulated readings from the HARPS instrument and its even more powerful successor, ESPRESSO, the Echelle spectrograph for rocky exoplanet and stable spectroscopic observations, also housed at the Very Large Telescope in Chile. They were digital archaeologists searching for long, slow, undulating patterns buried beneath the more obvious discoveries, convinced that the Proxima system had not yet given up all of its secrets. It was an Italian astronomer named Mario Damaso who, along with his team, noticed the faintest of trends in the long-term data. It was a subtle, slow drift, a wave with a crest so long and shallow it was almost imperceptible. This was not a signal that repeated every few days, but one that seemed to take years to complete its cycle. After carefully subtracting the powerful signal of Proxima b and meticulously modeling out the noise from the star's own activity, the pattern solidified. It was the ghost of a second planet, one with an orbital period of roughly 1,900 days, or a little over 5 Earth years. A 5-year orbit implied a planet that was much farther out from the star, and the amplitude of its signal suggested it was also significantly more massive than Proxima b. In 2019, the team announced the candidate planet, and in 2020, its existence was stunningly confirmed. Using an instrument called SPHERE on the Very Large Telescope, which is designed for the incredibly difficult task of directly imaging exoplanets, astronomers managed to capture a faint speck of light, a single pinpoint in a photograph, at the exact position predicted by the radial velocity data. They had not only detected the wobble, they had now seen the world responsible for it. This new world was named Proxima Centauri c. Proxima c is a world of a completely different character from its inner sibling. It has a mass of about 7 times that of Earth, placing it in a class of planets known as super-Earths or sub-Neptunes. It orbits its faint red sun at a distance of about 1.5 astronomical units. This is roughly the same distance that separates Mars from our own sun. But orbiting a star as cool and dim as Proxima Centauri, this distance consigns it to an existence of profound cold. It lies far outside the habitable zone, in a region where liquid water is an impossibility. The feeble warmth it receives from its distant crimson star would leave its surface at a temperature of around -230 degrees Celsius, which is a staggering -390 degrees Fahrenheit. This is colder than any natural temperature ever recorded on Earth. It is a true ice world, a frozen, silent globe where gases like nitrogen and carbon dioxide would exist as thick layers of frost and ice on the surface. Its discovery, however, was revolutionary. It proved that Proxima Centauri was not just a star with a single planet, but the host of a true planetary system, with worlds of different sizes at different distances. It also presented a major puzzle for theories of planet formation. It is difficult for models to explain how a planet of this size could have formed so far away from a low-mass star like Proxima, where the raw material of the protoplanetary disk should have been scarce. Yet, the story of this miniature solar system was still not complete. The incredible precision of the espresso instrument allowed another team, led by João Faria, to probe the data for signals even fainter than those of Proxima C. They focused their attention on the region even closer to the star than Proxima B. And in 2022, they announced the discovery of a third world, Proxima Centauri D. This discovery was a testament to the absolute limits of modern technology. The gravitational tug of this new planet was so minuscule that it caused Proxima Centauri to wobble at a speed of just 40 centimeters per second, which is about 16 inches per second, a velocity slower than a casual human walk. This tiny, almost insignificant signal was successfully extracted from the stellar noise, revealing a planet that is a true lightweight. Proxima D has a mass of only about 1/4 that of the Earth, making it less massive than Mars, and one of the lightest exoplanets ever found using the radial velocity method. It whips around its star in a blistering orbit of just over 5 Earth days, placing it inside the orbit of Proxima B. At this proximity, it is far too hot to be considered habitable, a scorched rock perpetually bathed in the unfiltered radiation of its parent star. With this third discovery, the portrait of our neighboring system was finally filled in. We now see a rich and complex family, a tiny, scorched sub-Earth on the inside, a potentially temperate but tidally locked world in the middle, and a large, frozen super-Earth in the distant outer darkness. Our closest stellar neighbor is not a lonely star, but the heart of a diverse and dynamic system, a complete solar system in miniature, beckoning to us from across the void. With the map of our nearest stellar neighborhood now so richly detailed, the question was no longer simply what was there, but could we ever hope to bridge the 4 light-year chasm and see it for ourselves? That question of whether we could ever hope to bridge the 4 light-year chasm and see it for ourselves is one that has shifted from the realm of abstract fantasy to the subject of serious, tangible engineering. The discovery of a diverse planetary system around our very next star has acted as a powerful catalyst, transforming Proxima Centauri from a mere astronomical curiosity into a destination. It has become the focal point for humanity's most audacious dream, the dream of interstellar travel. For the first time in history, we have a compelling, specific target for our first journey beyond the cradle of our own sun. Yet, to speak of such a journey is to first confront a barrier of distance so profound it is almost a different kind of reality. Our fastest spacecraft, probes like the Voyager and the Parker solar probe, travel at speeds that are astonishing by human standards, tens of thousands of kilometers per hour. But space does not yield to human standards. If we were to aim our swiftest probe, the Voyager 1, which is currently hurtling out of our solar system at over 61,000 kilometers per hour, or about 38,000 miles per hour, towards Proxima Centauri, its journey would last for more than 75,000 years. Civilizations would rise and fall on Earth in the time it would take for that lonely machine to cross the void. Chemical rockets, the technology that carried us to the moon and powers all our planetary exploration, are fundamentally inadequate for the task. They are simply the wrong tool, like trying to cross an ocean in a rowboat. They require carrying all of their fuel with them, and the sheer amount of fuel needed to reach even a fraction of the speed of light would be impossibly large. Even the more advanced concepts, like nuclear fusion rockets that would harness the power of a miniature star, remain firmly on the drawing board. Their immense technical challenges, likely decades, if not centuries, away from being solved. A journey to Proxima requires not just an improvement on our current technology, but a complete and total revolution in our thinking about propulsion. That revolution received its most dramatic and well-publicized blueprint in 2016, the very same year that Proxima b was discovered. In a stunning announcement, a project called Breakthrough Starshot was unveiled to the world, backed by the physicist Stephen Hawking and the entrepreneur Yuri Milner. It was a proposal so audacious, so far beyond our current capabilities, that it felt like it had been pulled directly from the pages of a science fiction novel. Yet, it was grounded in physics that was fundamentally sound. The core idea was to abandon the concept of a large, heavy, fuel-laden spaceship altogether. Instead, we would send an entire fleet of incredibly small, ultra-lightweight probes. These would be nanocraft, tiny robotic explorers called star chips. Each one would be a fully functional space probe, complete with cameras, sensors, navigation thrusters, and communication equipment, all miniaturized onto a silicon wafer no larger than a postage stamp and weighing only a few grams. This tiny craft would be attached to a light sail, a gossamer-thin sheet of advanced material, perhaps 4 or 5 meters across, or about 13 to 16 feet. This sail would be the probe's engine, but it would not be catching a stellar wind. It would be catching a beam of light from home. The Starshot concept envisions the construction of an enormous laser array here on Earth, likely in a high-altitude desert like the Atacama, the same place where Proxima's planets were discovered. This would be a phased array of lasers, all firing in perfect unison, covering an area of at least a square kilometer, or about 4/10 of a square mile. Together, they would combine their beams to form a single colossal beam of coherent light, with a power of up to 100 gigawatts. To put that in perspective, that is roughly the power output of all the world's nuclear power plants, combined, focused onto a single point. This beam of pure energy would be aimed at one of the nanocraft's light sails, which would be waiting in orbit high above the Earth's atmosphere. Light, though it has no mass, carries momentum. When photons strike the sail, they transfer that momentum, giving it a tiny push. But when the beam is 100 gigawatts strong, those tiny pushes combine into a relentless, overwhelming force. For the few minutes that the beam was focused on the sail, the tiny craft would undergo an acceleration of thousands of Gs, a force that would crush any human astronaut, but which a tiny chip could be engineered to survive. This hurricane of light would accelerate the nanocraft to a speed of about 20% the speed of light. That is a velocity of 60 million meters per second, or over 134 million miles per hour. At this incredible speed, the journey to Proxima Centauri would no longer take 75,000 years. It would take about 20 years. A human generation could witness the launch and arrival of humanity's first interstellar emissary. The nanocraft would not slow down upon arrival. There is no known way to carry the fuel required for such a maneuver. Instead, they would scream through the Proxima Centauri system at 1/5 the speed of light, a frantic flyby lasting only a few hours. In that brief window, their cameras and sensors would be working furiously, capturing images of the planets, analyzing the light from Proxima B's atmosphere for the chemical signatures of life, measuring the system's magnetic fields, and gathering as much data as physically possible. This precious information would then be beamed back to Earth using a small onboard laser, a faint whisper of a signal that would itself take 4.2 years to cross the void and reach the telescopes of home. The technological hurdles are, of course, immense. We do not yet know how to build a laser of that power and stability. We do not have a material for the light sail that can reflect the beam's energy without instantly vaporizing. We do not know how to protect a probe traveling at such speeds from collisions with interstellar dust grains, where an impact with a particle as small as a grain of sand would be a cataclysmic, explosive event. We do not know how to aim the beam with such precision, or how to communicate with the probe and receive its data across such a gulf. But these are now engineering problems. They are no longer questions of pure fantasy. The Starshot Initiative has provided a roadmap, a set of challenges for a generation of scientists and engineers to solve. With the discovery of its worlds, Proxima Centauri ceased to be just a neighbor. It became a destination, a tangible goal that is pulling humanity's gaze outward, urging us to take the first tentative steps on the path that may one day lead us to the stars. That path began not with a starship, but with a flicker of insight in a darkened observatory. Our journey through this story has mirrored humanity's own journey of discovery, a voyage that has transformed a single, unremarkable point of light into a rich and complex solar system. We began with Robert Innes, a man whose patient eyes found a ghost moving in lockstep with the brilliant Alpha Centauri, and in doing so, redrew the map of our cosmic neighborhood in 1915. This faint ember, officially named the closest star to our sun, was then revealed to be a red dwarf, a star of almost unimaginable longevity, destined to burn for trillions of years. A quiet witness to cosmic epochs yet to come. This is the story of how the invisible became not just visible, but vital. A silent neighbor who finally broke its silence, not with a sound, but with the gentle, rhythmic tug of unseen worlds upon their sun. And what worlds they are. The unearthing of Proxima Centauri b in 2016 was a moment that captured the global imagination, presenting us with the tantalizing prospect of a rocky world, just slightly more massive than our own, orbiting within the precious habitable zone. Yet, as we have seen, this initial hope was swiftly met with the harsh realities of a world bound to a volatile star. We were forced to confront the dual nature of Proxima's embrace, an orbit close enough for warmth, but also close enough for the sterilizing fury of its solar flares and the relentless grip of tidal locking, which may have carved the planet into hemispheres of eternal fire and perpetual ice. Then came the wider view, the discovery of the frozen, distant super-Earth, Proxima c, and the tiny, scorched inner world of Proxima d, completing the portrait of a system far more diverse and intricate than we had ever dared to imagine. Our nearest stellar neighbor, it turns out, is not a simple hearth, but a complex and challenging environment, a celestial laboratory demonstrating that the conditions for life may hang by the most delicate of threads. This detailed portrait of a neighboring system has done more than simply add entries to our catalogs. It has given our oldest dream a concrete address. The 4 light-year journey, a distance of 40 trillion kilometers, or about 25 trillion miles, no longer feels like an abstract impossibility, but like the next great ocean to be crossed. Ambitious projects like Breakthrough Starshot, which propose to send gram-scale nanocraft on a 20-year voyage powered by light itself, represent a fundamental shift in our ambition. They are the modern equivalent of the first sea charts, sketches of a new world that invite us to build the vessels capable of making the journey. The challenges remain monumental, pushing the very limits of our physics and engineering. But the destination is no longer a vague point in the infinite dark. The destination is Proxima Centauri. So concludes our journey, for now, to the star next door. From an anonymous flicker on a glass plate to a dynamic family of worlds, the story of Proxima Centauri is a profound lesson in perspective. It reminds us that the universe does not always display its greatest treasures in the brightest showcases. It teaches us that our closest companion is a quiet, ancient, and often violent star, a world maker that offers both the promise of habitable conditions and the threat of cosmic annihilation in the same breath. Proxima Centauri stands as a silent testament to the vast, unexplored frontier that begins just beyond the edge of our own system. It is a constant gravitational pull on our curiosity, a destination that fuels our science and our stories, a faint red beacon in the beckoning darkness, waiting patiently for the day when its nearest neighbors finally decide to pay a visit.